Okay, here's some review problems from Trig that you are expected to know for the AP exam, and you will start to see these problems as you start to find the exact area under the curve. So for the first one, it's sine of pi over 4. Remember to change any radian degree to, from any radian measure to a degree measure, you multiply by 180 over pi. So in this case, this is equivalent to 45 degrees. So we got to think about the 45, 45, 90 triangle, the ratios in that triangle, and they are x, x, x radical 2, or some of you may know it as 1, 1 radical 2. And so you want to find the sine of 45, so using SOHCAHTOA, opposite of hypotenuse, you realize this is x over x radical 2, which the x's cancel. So you get 1 over radical 2. And if you rationalize that, that becomes radical 2 over 2. So you should be able to do it that quickly and easily anytime you see that problem on the AP exam. So another example, cosine of pi over 6 is the same as the cosine of 30. So I need to know the ratios in a 30, 60, 90 triangle, which are x is opposite to 30, the hypotenuse is double that, and the third side is x radical 3. That's how I memorize that. And then I do the cosine of pi over 6, which remember is the cosine of 30, adjacent over hypotenuse. So x radical 3 over 2x, where the x's cancel, and I get radical 3 over 2. Tangent of pi over 3 would be tangent of 60. So using the same triangle up here, I am now imagine standing up here, because that's where the 60-degree angle is. And tangent then would be x radical 3 over x, which again the x's cancel, and I get radical 3. So as long as I can memorize these two triangles, I should be able to find sine, cosine, and tangent of any angle that they give me on the AP exam quickly and easily without a calculator. Other trig functions that you need to be aware of, that you need to be able to do in your head, usually involve the sine curve. If you notice, this is the y equals sine of x, okay, or f of x equals sine of x. And as long as you can visualize this, you should be able to come up with, for example, the sine of pi over 2. As long as you can see that, you can see, oh yeah, that's the top of the mountain, so that's got to be 1. Or say the sine of pi, which you say, okay, that's when the comes back down and hits the x-axis is 0. The other common ones are sine of 3 pi over 2, which again, if I can visualize this, I should see that that's negative 1. And then both sine of 0 and sine of 2 pi, I see as hitting the x-axis as being 0. So those are the four what we call quadrantal angles that you need to be familiar with and be able to do in your head by visualizing this curve in your head. Likewise, that works with cosine also. If you notice, this is the cosine graph, okay? And I can actually find the cosine of all the quadrantal angles by using this picture here. But again, remembering that cosine of 0, which equals the cosine of 2 pi, which is 1. So those are two that you need to be aware of by thinking about this function. And if you can remember, visualize this, you can see, oh yeah, the cosine of pi over 2 has to hit the x-axis, so it has to be 0. The cosine of pi has to go down below the axis, is negative 1. And the last one you need to be aware of is cosine of 3 pi over 2, which again hits the x-axis, so it would be 0. So these are the 5 quadrantal angles that you need to be aware of for both sine and cosine that are commonly asked in the AP exam on the non-calculator portion of the test. So you've got to be able to do this without a calculator. Okay, so let's see if we can do the fundamental theorem with these problems. Find the exact area under the curve using the fundamental theorem of calculus, okay, which I abbreviate as FTC. Now remember, the fundamental theorem of calculus means to antiderive your function, take your two bounds and substitute them, and subtract the top function minus the lower function. And so I'm going to do some notation here, make sure you're familiar with that. The antiderivative of secant squared x, which is the function in between my parentheses, remember this is like my left parenthesis, that's my right parenthesis, is tangent. And I'm going to evaluate this from the upper function, pi over 4, minus the lower function, pi over 3. And we see now that we don't have to worry about the plus c, because when I take the upper function minus the lower function, the c minus c will always cancel. So we acknowledge the fact that we don't need a plus c by putting in this symbol, the evaluated symbol. This tells the reader, whoever's correcting your test, that you understand there's a plus c, but you also are telling them that you understand that that will disappear and that you're not going to worry about it. Okay? Normally without this, we'd have to put the plus c. So then if I plug in the two bounds, I get the tangent of pi over 4 minus the tangent of pi over 3. And as you saw before, you should be able to solve these pretty quickly and easily in your head by visualizing the two triangles. Pi over 4 is a 45, 45, 90 triangle. So the tangent of pi over 4 would be opposite over adjacent, which is 1. X over x, or 1. Tangent of pi over 3 is the tangent of 60, and opposite the 60 is the radical 3, over the adjacent, which is 1. So it's 1 minus radical 3, and this would be my exact answer. If I had access to a calculator, I could actually punch that in and get the approximate number, but this is traditionally given on the non-calculator portion of the test. Okay, so let's see how that works for a non-trig function. So again, I'm going to anti-derive this equation. So 12x cubed, if I apply the anti-power rule, becomes 3x to the 4th minus x squared, evaluated from 0 to 2. So again, that evaluation symbol means I recognize there should be a plus c there, but I also know that when I subtract the upper bound minus the lower bound, the c's will cancel. So it's kind of an extraneous step that goes away, so we acknowledge that by not putting the plus c there. So we plug in 2 and we plug in 0. So 3 times 2 to the 4th is 48, minus 2 squared is 4, minus, in this case you get 3 times 0 to the 4th minus 0 squared, which is still 0. And so my answer here would be 44. And this would be the exact area of this curve between the bounds of 0 and 2. Okay, last problem here is another trig function here. Okay, so if you notice 5 sine of x, remember when there's a number out front of it, we can actually imagine and bring it out in front, ignore it, anti-derive what's left, and then just make sure to multiply the answer at the end. So the antiderivative sign, you've got to be careful, is actually negative cosine of x, evaluated from 0 to pi. Remember, we have that 5 out front there, so we actually want to make this negative 5 cosine x, evaluated from 0 to pi. So this would be negative 5 cosine of pi minus negative 5 cosine of 0. And again, these are two quadrantal angles that you should be familiar with by thinking about the trig function or the graphs. So cosine of pi, remember, starts at 1, goes down to 0, goes to negative 1. So this will actually be negative 5 times negative 1, which is positive 5. Cosine 0, remember, is 1, so this will be plus 5, because minus a negative. 5 times 1 will give me 5. So the area under the curve here would be equal to 10. And that would be the area of this, the exact area of this particular function between 0 and pi. Okay, so a couple more examples. Antiderivative of x to the 4th is equal to 1/5. X to the 5th, evaluated from 1 to 5. That's usually how you say that. Again, that evaluation symbol acknowledges the plus c is supposed to be there, but it will also cancel when I subtract the upper bound minus the lower bound. So then I do 1/5 times 5 to the 5th minus 1/5 times 1 to the 5th. And this would be 625 minus 1/5 which would be equal to 624.8. This would be the exact answer. Okay, next problem. The antiderivative of cosine, remember, is sine of x, evaluated from negative pi over 2 to negative 3 pi over 2. So I see quadrantal angles coming up here. Okay, so that if I do the sine of negative pi over 2, minus the sine of negative 3 pi over 2. And I got to think about negative pi over 2. So that's going backwards on the sine curve. This will actually be negative 1. And then negative 3 pi over 2 would actually be positive 1. So I'll get negative 1 minus 1, which will come out to be negative 2. And so this part of the curve is actually below the curve in order for the area to come out to be negative. Okay, last problem here is kind of a unique problem here, but let's antiderive x cubed, which will be 1/4 x to the 4th, evaluated from negative 2 to 2. And when I do 1/4 times 2 to the 4th minus 1/4, oops, that should be a 4, times negative 2 to the 4th, you'll notice that I get the same answer in both cases. I get 8 minus 8, so this area is actually 0. And how can it be 0? Well, it turns out x cubed is symmetric about the origin. So if I were to look at the graph of this function, I would see a graph that looks something like this. And so from -2 to +2, you can see that the area here to the left exactly matches the area to the right. And so the positive section actually cancels out the negative section, and that's why we get an area of 0. So it actually does make sense, even though it's kind of strange to actually find an area and have it turn out to be 0. Okay, here's some applications of the two theorems that we've been looking at. One is the mean value theorem. The second one is the intermediate value theorem, i.e. the temperature problem here. So what I'm going to do here is notice that the first problem is a mean value theorem, because if I look here, I see that phrase I'm supposed to remember for a mean value theorem, which is derivative equals slope. It's kind of hidden there, but that cues me in that this is a mean value theorem. So I want to find out where the derivative equals 0, which means I actually want to find out, is there a value interval where the slope equals 0? And if I look here, I can see that, remembering that slope is always y2 minus y1 over x2 minus x1. And the only way that's going to happen is if the numerator is 0. And if I look here, I can see, oh, those 2 points I can actually do the slope formula for. 0 minus 0 is my 2x values, 2 y values. 9 minus 4.5 is my 2 x values, and I can see, oh, I get the 0. So the interval in which the derivative is equal to 0 would be from 4.5 to 9. This interval, the mean value theorem, would apply, and so this is the answer to my question here. Last problem here is a intermediate value theorem. It's asking for a value 100 if this equation could actually equal 100. And the trick to this is actually to plug in 2 into this equation, plug in 5 in that equation, and see if 100 comes in between those two values. Well, 3 times 2 squared, so f of 2, would be 12 minus 7 is 5. And 3 times, if I put 5 in there, 5 squared is 68. So the f of x will not equal 100, because if you notice, 100 does not come between 5 and 68. So it will not equal 100 between 2 and 5. And I can actually prove that by taking this equation and solving, by taking 3x squared minus 7 equal 100 and solving. I get 3x squared equals 107. X squared equals 35.6 repeating. And if I square root both sides, I'll get x equals 5.97, which if you notice is outside the range between 2 and 5. So I would have to say no, the f of x cannot equal 100 between the values x equals 2 and x equals 5.